So let us discuss a question from thermodynamics. This is a question on Rankine cycle. So let's draw Rankine cycle first. This is on a TS diagram. So you have a TS diagram where there's a liquid to vapor change. Okay, and Rankine cycle basically has all these regimes. So this is a point 1. Let's first draw the pressure on which it operates. So this is your one of the pressure line. These are how the constant pressure lines look in a TS diagram. Okay, within the domain there are horizontal lines, and elsewhere they are just a quadratic function. So we start from here, which is 1 to 2. The work is done on a saturated water, liquid water. Work is done by the pump where it enters the boiler, and there's a heat addition that takes place. Because of the heat there's a change from liquid to vapor, and it is given that the higher pressure side of the cycle at a supercritical pressure, so it's in the supercritical region, so this is 0.3, and then the state properties are given, and so then you have the reversible, then you have the turbine expansion. The exit of the turbine is always a wet mixture. There is some amount of there is some water in the liquid form, though it is almost 0.9 or 0.85. The dryness fraction is 0.85 or 0.9, but there is always it's a wet stream, so we assume that 4 is inside the domain, and then there's a condenser. So 1 to 2 is a pump, 2 to 3 is a boiler, 3 to 4 is a turbine, and 4 to 1 is your condensation. So pump work is given, so basically work 1 to 2. Now work in a pump, work done by the pump is increase in enthalpy, and that is H2 minus H1. Now this can be derived, or this is just a consequence of when you apply a first law for open system. So H2 minus H1 is work done, and that is 30.54, and H2 is something which we don't know. Okay, but H1 is basically at the condenser pressure, which is 5 kPa. This is 5 kPa. Okay, and this is 30 MPa. Okay, so at 5 kPa you have H1 is nothing but your HF at 5, right? At 5 kPa. So this is H2 minus H1 at 5 kPa is 137.82. Okay, so H2 is basically, when you add 137.82 plus 30, so that gives 168.36 kilojoules per kg. So this is H2. So we got H1, H2. Let's find out H3, H4, so that then we can compute work done, anything. Okay, so let's look at H3. Now H3 is basically given because H3 is a supercritical, it's in the supersaturated zone. Okay, and as we need to call supersaturated actually, and H3 is given as 3275.36, so that is given. But now how do I get H4? Now remember that H4 is basically HF at 5 kPa plus, because it's a wet mixture, so you need to have some portion of vapor and some portion of liquid. So HFG at 5 kPa. Now we know this HFG and HA 5 kPa, but what I don't know is the dryness fraction value. So for this we also use a property of this process 3 to 4. Now 3 to 4 is a reversible adiabatic processes, so S3 is equal to S4. S3 is something which is given. S3 is at 30 MPa. The value of specific entropy, that is given as 6.0342, and S4 again it's a wet mixture, so we can write SF at 5 kPa plus X into SFG at 5 kPa. So this is a complete Rankine cycle problem. So SF at 5 kPa is, let's look at the values. It is 0.4764, 0.4764 plus x into 7.9187. Okay, so you can see that if the entropy, if the 0.4 is in 0.4 has to be inside, because if 0.4 has to be outside the dome, the entropy has to be at minimum of 7.91, but the entropy of 4 has to be entropy of 3, and entropy 3 is 6.03. So it is inside, right? There has to be some x which is less than 1. Okay, so from this we get a dryness fraction of 0.701. 0.70186 is the dryness fraction. So once I get that, I go and substitute in this enthalpy equation, where HF is given as 137.82 plus dryness fraction 0.70186 into 24. Let's look at the value again. 2423 is the HFG, 23.66. So the whole thing is about getting the dryness fraction. Once you get, you can compute HF, which is 1838.86. So 1838.86 is the H4. So I got H3, I got H4, everything is known. So now work done by the turbine, I can get work done by the turbine is H3 minus H4, and H3 minus H4 is, H3 is 3275.36 minus 1838.86. So once you subtract, you get a value of work done which is 1436.5, okay, kilojoules. So I know WT. And what is QH now? Heat transfer. Heat transfer takes place in the boiler, so it's H3 minus H2, and we have already calculated that H3 is 3275.36 minus H2. H2 is 168.36. So we get QH as 3107 kilojoules per kg. So now what is asked is the efficiency, and efficiency is equal to work done by turbine minus work done by pump by QH, right? Okay, so work done by turbine we know 1436.5 minus work done by pump, which is given as 30 point. So let's look at the value again. The pump work is 30.54. So 30.54 divided by, I'm at the end of the page, so I'm writing slowly, 3107. Okay, yeah, so this ratio roughly comes about 0.4525. so 0.4525, so it's 45.25 percentage. So 45.25 percentage is the efficiency. So this is it. So we have done a complete Rankine cycle problem. Remember, Rankine cycle is very, very important. Always once in 2 years or 3 years, always there's a big 2 marks question, or there can be a linked question also, so 4 marks. So 45.25 is the answer. Thank you.